So let's start on, this is, well, it's 2019. And I've been using this question for quite some time. And the purpose of the assignment questions is literally just for you to take the time to try and understand. And the nature of these questions is usually a little bigger. So some of them are mathematical techniques, graphing, or the question itself is a little bigger and takes more time to think about. If you simply have the answers as written, it might look simple enough, but to go through the entire process could be a little bigger. So let's take a look at the question I'm thinking about. And it used to be 2018. I just reused the same questions. So this is number 1, and it's 2019 at the moment. So you have a sample of krypton, and it's going to expand reversibly, isothermally. So it's going to stay constant temperature for the expansion. It's done reversibly, which means you should think of the sand pile type of scenario from one volume to another. Tells us that the internal energy changes by this amount. We're told it's a virial gas, virial equation of state, and we're supposed to use it up to the second coefficient, and it's a B, not a B prime. So what that means is this is the one that's expanded out in terms of volume or molar volume. If it had a prime on it, the textbook would indicate that equation was expanded out in a series based on pressures. So, and we calculate the usual sort of suspects. Okay, so first things first. If I was attempting to do this somewhat correctly, I would have to draw sort of a picture. So we have this piston assembly, and it's going to expand. And if we're doing it reversibly, I need to put in the sand pile, because it would just make a little more sense talking about that. So we have the volume, 5.25, and that's centimeters cubed, which is essentially milliliters. So you take off 1 grain of sand at a time, and each time you so you take off 1 grain of sand, this piston is going to go a tiny bit. And any gas has a tendency of dropping temperature. Most gases have a tendency of wanting to drop the temperature. So if that happens, we have to wait. And what we would do is, any change in temperature that we witness when we take off 1 grain of sand, we wait for a new equilibrium to be established, where heat would probably go in. If it was an ideal gas, it's 100% guaranteed that the temperature drops when you expand. If it's a real gas, it's possible that tiny volume expansion, if potential energy of its interactions is strong enough, the temperature could hypothetically actually drop. And I'll talk a little more about that in a minute. So ideal gas, the temperature would drop guaranteed. But because it's a real gas, we have to be careful. Either way you shake it though, any gas, whether you expand or contract it, whether it's real or ideal, the temperature is going to have a tendency of changing. You may have this really weird real gas that for the size of the volume change you did, the amount that the temperature wants to drop versus going up, right, because of the energy that's transferred, could be equal, and there's no temperature change. But that's rare. So we go here, and eventually, I don't know how many grains of sand, so let's just say the pile got smaller, and the new volume is 6.29 centimeters cubed, which is mils. We're told the number of moles is 70 millimoles. 1, 2, 3. So I just have a tendency of wanting to write it in decimal form, unless it gets really small. And it's krypton, just in case I need to know that. And the temperature is 373 Kelvin. We're told that the internal energy was increased by 83.5 joules. Now, we're told it's a virial, so it's a virial gas, so I might as well remind myself from your reference sheet or whatever it is you want to call it, One of the ways of looking at it is using molar volumes up to the B term. So that's one way. The other way is to realize, that's thinking, molar volume by definition is simply the volume divided by number of moles. You can insert V over N in place of these, and what you could end up with would look like this. B N squared B R T over V squared. So some textbooks will only show you one and not the other. And when you do a little bit of integration on either one of these, it's slightly different. So it might look funny at first, but once you get used to it, you become more comfortable with it. So this is the virial gas pressure, right? That's the gas pressure. Okay, so we're asked to solve for, and one of the things that I do is, as soon as it's mentioned that your change in internal energy is this much. So these are just think bubbles right now. One thing I know for sure is that the first law of thermodynamics is this one. And again, this is always true. Pink. So we do know that one. We're asked to solve for these two. Now it makes sense to me that when you're taking sand grains off of this and the volume starts changing, and we did talk about it, the temperature of this gas, real or ideal, wouldn't have mattered, is very, very, well, is going to change. If it's a real gas, there's a weird chance where the volume changes is equal and offset the temperature changes it wants to do. But that's rare. So the point is, to keep this temperature constant, you're going to have to let heat either go in or come out as you go to keep that temperature the same. So there's going to be some heat flow. You have a volume change. And one of the other things we know is the fundamental definition of work is expansion work when there's a change in volume of a gas, if there was an external pressure, which we're led to believe there is. Yeah, because think about it. Even though it doesn't state what the pressure is at the moment, what we do know, think about it, because only a grain of sand is removed, whatever this sand pile exerts as an external pressure, your gas, right? These two pressures are essentially, because of that word reversible process, the pressure external is pretty much matched to whatever the gas pressure is all along the way. So you take one grain of sand off. The external pressure is ever so slightly smaller than the gas pressure. So as a result, being this one stronger, it's going to go, move it a smidgen. So now the two pressures become equal again. So they're never ever far out of sync. So in this formula, we could replace this external pressure with the gas pressure, and because it's virial, do you see how we have two different ways of doing this integral? So it stands to reason right off the bat we can calculate this with some integral calculus. So why not? We can see clearly that we're going to have to do that, or could do it. Maybe there's another way, so we never have to panic. It's possible, after thinking about it, that we could have calculated Q, right? Possibly, if that's the case. If we could have, then we could have gotten work through this one. But it looks like this is doable. So why don't we do these two? I'll set it up side by side. So I'll split the page, and I'm going to do this. We're going to calculate the work using these two different ways of doing it. So I'll put, let's put the molar volume one over here. So we'll solve it using molar volume for pressure. And over here we'll do sort of the normal just volume with moles separate. And N squared BRT. So I'll set it up. And I would say a couple of things first. If I was to start off with this, that's the change in volume. So this right here is just V volume. So a little think bubble is going to say molar volume is equal to V divided by N. And in Calculusville, we say the change in volume. So I want to get that V by itself over here. Bring the N over. So N times molar volume is equal to volume. Now, when we talk about changes, now in this problem, is the number of moles of gas constant? And the answer is yes. So if I start asking the question using that little infinite D symbol, so let me say this, D changes in this left-hand side equaling what changes are going to happen in the right-hand side. So that's what this says in calculus. Now, N is constant, so we take that out. So you get N dVm is going to be equal to the change in volume. So I can replace the dV of the gas with this. And the pressure external, I can put in place of that this right there. So what that's going to look like if I rewrite it over here, and I guess I'd show a couple of steps. You'd have RT over Vm plus BRT Vm squared. And then we replaced the, sorry about that, I'm not paying attention to where the camera can see it. So I've replaced in place of P external what is equal to the pressure of the gas virial in terms of this one. So what I've circled will go in place there. The dV gets replaced with NdV molar. Now this N gets distributed into each of the terms. And the other way of looking at it too, well, I'll distribute it in. So we'll go show a couple steps here. So you would get nRT over Vm plus nBRT over Vm squared dVm. So I'll go one more step and then I'll let you guys finish this out. What's constant? And we do realize that because these two terms are separate, you could integrate this first term and integrate the second term, almost as if the second term, even as if they're separate. Keep them all together. If you need help with that, come see me later. But nRT are constants, they come out. Even that B is a constant. So technically, if I was to break this up into two terms, why don't I do that? I'll break it up into two terms. The first term would be minus nRT integral 1 over Vm dVm. The second term, and that negative will go with it, right? nBRT, and you're going to integrate 1 over Vm squared dVm. So that transfers to this, and I think both of you, all of you should be able to know how to do this integral, right? And I think, why don't I just go ahead and show that? The integral of 1 over V is ln Vm, and you're going to be doing it between initial and your whatever your second final volumes are, right? So this first term is going to be minus nRT, right? And you'll get ln V2 over V1. So that term becomes that. This one, I'm going to leave that negative. This negative. Well, first of all, let's think about this. What does this integrate to? So this is you thinking, bing, 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 bing. If you were in calculus class and it said you've basically got x to the negative 2. See how that's Vm to the negative 2 if you write it this way, and dx. So the integral of this is you're going to increase it to become negative 1, and you have to divide by the new exponent. So you're going to get negative 1 over x. So you're going to get a negative. So you're going to get negative 1 over Vm with these two limits. So that negative will come out, turning that into a positive, and then you'll have nBRT, and then what you'll have is 1 over V2 minus 1 over V1. And these are Vms. Right? These are molar volumes. right? Don't let me, those are VMs, so don't drop the M, Mike. Okay, so that looks correct. I'm just kind of double check. So this tentatively, I'm doing this cold here, tentatively to me looks correct. And remember how we always said at the very beginning when we introduced work, did I or did I not say when you do this, you should complete this formula for ISO, for example, isothermal and reversible process. Complete this for 3 different gases, right? Ideal, virial, van der Waals. So would everybody agree that for isothermal reversible expansion of a virial gas in terms of VMs, this would be your formula right here, how to calculate it. Formula in a box. So you could sub in and you should get a number. And let me just say that the number you should get from this, I'll ballpark it rather than give the exact number, but the ballpark number for this, let's just say that the answer is going to be somewhere in between, so, well, it's going to be a negative number, and it's going to be somewhere in between minus 50 and 0. So if your number is not in between there, you know that something is not right. So I don't want to give the exact number away, but it's a negative number of joules. If we had done this one, what are we looking at here? So if we had chosen this one, which is just volume, you're going to get, so I'm trying to peek ahead at looking at enthalpy, trying to think of 2 things at once here. That's why my brain stopped for a minute. So we're going to put this in place of that pressure. And that's already in volume, and this is already in volume, so I guess we're pretty much ready to go here. So the work is going to equal negative integral, and it will be from whatever the initial to the second volume is, nRT over V plus n squared BRT over V squared. And that is dV. So I think you can see how the integral of this one and versus that one, you're going to get nRT and that, those are all constants, they can come out. So you might as well say that looks like you had to do this integral. nRT integral 1 over V dV from V1 to V2 plus, that negative will carry over when you split up these 2 terms momentarily. Right, that negative applies to this one, and it also applies to this one because it was way out in front of whatever was here. N squared BRT, constants, 1 over V squared dV. And I think you can see where this is going. It's going to look very much the same as this one. The only difference is going to be the number of n's that are out front. So this one will be minus nRT. Yeah, it's going to look very much the same. So this will be ln V2 over V1. This integral gets a negative, just like it did over here, so you're going to get plus n squared BRT. Wait a minute. Double checking here. Yes. I just balked at it myself. I'm like, oh my god, that's n squared. So this is correct. That's correct. That's correct. Yes. And this would be 1 over V2 minus 1 over V1. So let me just think about that. That does look correct. And it will lead to the exact same number, either way you did it. So the 2 formulas in a box could look slightly different. This is the one if the molar volume is given. This is the one if it's just volume. So you see there's a slight difference in the number of n's. Look at it mathematically this way. This term, see how you have the ln? So the ln terms, the units cancel. So it stands to reason that you should have 1 n here, and even if if these are molar volumes or just volumes, because it's trapped inside of a lawn, those units have to go away completely. So in order to get just joules, these have to be the same. But see over here? See how this is not inside of a lawn? So these units of liters per mole, those per mole units are still going to survive and need to somehow cancel something out when you compare this one to this one. That's why you need the extra n's have to appear here, squared. So that takes care of the work. And the interesting thing is, think about it. And this is where I'm thinking ahead a bit here. So now think bubble. We know this is absolute, always true. We know that, and we know that. So that means that the heat will equal delta U minus the work. And the delta U, was a plus 83.5, right? And we're subtracting off a negative number that we calculated for the work. So that's a plus. So this number in joules, and that's in joules, this number in joules has to be bigger than 83 because you end up adding more. Okay? So you can get Q. So at this point, all that remains is enthalpy. So what I'm thinking about here is enthalpy. What do we got for enthalpy? Well, there's a couple ways of approaching this, I guess. If I bring up this is pretty much what you have in your student notes, because all I'm doing is I'm looking at enthalpy, right? So that's the definition of enthalpy. And what we have already seen because of this, right here, is we've seen permutations like this. So what I do know is we have the internal energy so far. Is it possible in this question to just go after what the change in the quantity P times V is? We know the volume has changed. We know the pressure has changed. So both of them are changing. One way of looking at it is in your notes, and this is what can trip you up every single time. These are the notes that talk, see that word right here? Ideal gas. If it's an ideal gas, you can talk about the changes of the left-hand side, PV, and the changes on the right-hand side. But remember, this is a virial, so you can't use this in place of that because it's a virial, right? So if we wanted to go this route, we'll have to take a look and draw that out and see what that looks like. The other thing we could do is we could say, we could look at this different way of looking at it. We knew that a change in enthalpy was related to a pressure change through this thing. But if there's no temperature change, because it was a constant temperature process, do you see how this term is dropping out? So for this question, technically, you could calculate enthalpy based on something like this, mu T, dP. Do we have that? Could we calculate for a virial this nonsense? And the answer is, I'm looking at it. Ooh. Man. Calculating the volume as a function ultimately of P could be really nasty. We could get this value for a virial. The volume has changed. So you see how does the volume change as the pressure? So coming up with an integratable entity like this, you'd have to have this V, and these two terms would both have to be V as a function of P. Yeah. Which looks hairy to me at the moment. So I'm thinking that this doesn't look good either. Okay, so what else do we have? I guess we could say, if we looked at the change in enthalpy, du plus dpv. Let's expand this out for a second. We know this one in the integrated form, so we can leave that as it is. Let's split this up. So you could have V dp plus P dV. Now, isn't it interesting, folks? Now think about this. By definition, in a reversible process, do you see this quantity here was gas in gas? But if it turns out it's reversible and the pressure of the gas happens to equal the external, do you see how this quantity right here will literally be the work? So we know this quantity, we know this one. So can we do that? Well, so let's just take a look at that term. Could we go after the integral from V1 to V2 of simply just this? So we look at that and we say to ourselves, in the world of the virial, we had already seen nRT over V plus n squared bRT over V squared, correct? Do you see that? Can you isolate V by itself so that you can put it here and integrate it? And the answer is crap. We can't integrate this because it's trapped inside there. Wow. So I'm guessing what we're going to have to do is jump back up to here. And we're going to have to say, okay, let's integrate this and go after this quantity. So what is the change? So what this means now is, can we go after I'm thinking, can we go after this? Another way of looking at it is to say, can I get, if I take this virial and I multiply both sides by V, right? I'm going to get a PV term over here. So I could get PV of a virial. This term would lose its nRT plus n squared PRT over V. So now I'm going to say, how is this quantity, how is this side changing? How is this term changing through the process versus how is this term changing? So how is the PV quantity on the left-hand side changing? What's happening over on the right-hand side? Well, what do we know about this process? Are the moles changing? No. Is the temperature changing? No. So no change applies to this term in our process. So that term's gone. So this quantity for a virial will be equal to this. So I guess technically, all this is constant, but what you're going to get is the change in 1 over V. And in this question, it's going to be 1 over the second volume minus 1 over the first. So the change in the quantity PV for the virial gas, if it's isothermal, constant temperature, and reversible, that's why that drops out, will equal this. So folks, I guess that's going to do it. This we can calculate. It'll go in right here. We already know that, and you'll get that. So I think I've just built this. You would get n squared bRT 1 over V2 minus 1 over V1. That should do it. Yeah. And the number you're going to get for, I don't want to give it away. So you're going to get a positive number here in joules. And that number is going to be somewhere between 50 and 150. So somewhere in there. So if your number doesn't fit in this range, you know it's probably incorrect or a typo or some damn thing like that. But so is that it for the question? I'm lost in space here. And the answer is, I believe it is yes. So that does it for question number 1, and this is what, 2019? Maybe I'll renumber it later, but this is a rough way of approaching it.